comments from everyone. And that's it. If we go a little bit beyond the 1 hour, is completely fine. So do not feel that you have to rush. Augusto, did you give Alessandra the co-host privilege so that she can share her screen? So feel free, Alessandra, to bring up. To actually bring up at least your slides to make sure that we see them and it works just fine. And then I'm gonna simply announce what the two of you do. So right now I do not see your slide. Okay, yeah, it seems to be good, fine, and we can hear you. So wonderful. So it's very exciting presentations we have today. I have the great pleasure of having two professors from Europe today presenting. So the first one is Professor Alessandra Faggian. She's from Graz Science Institute in Italy. And as you can see from her first slides here, she's going to speak a little bit about artificial intelligence and regional eco-innovation. And then in the second part of the presentations today, we're going to have Professor Stefan Borsky. He's from the University of Graz in an institute which is specialized on climate change. And it's obviously in Austria. And you will see in the second part of the hour that he's going to focus on questions related to weather shock and global supply chain linkages. So Alessandra, it's all yours. Thank you.
Thank you very much, Sandy, and thank you for the invitation. So for those of you that know me a little bit, this is not a topic that I normally work on because I do a lot more about human capital, local labor markets. I've done some work on innovation, but not on artificial intelligence before. But I'll tell you in a second why actually I started caring about this topic. First of all, some of my co-authors are experts on regional eco-innovation, and the one from the University of Milan, has been working on artificial intelligence for quite a bit. And artificial intelligence is becoming really a key word, right? One of these fashionable words everybody's talking about. And in fact, here is just to give you an idea of how many entries you actually get on artificial intelligence if you actually try and Google it. Sorry. So there is a huge hype around these terms. But also what we've noticed is that it's not just a media hype. There is an academic interest that is growing exponentially when it comes to artificial intelligence paper. And this is from 2000 to 2015. You can see how many more papers have been published. This is the source is Scopus on this topic. And of course, among the artificial intelligence paper, there are some topics that are more used than others, such as machine learning, for instance. It's another key topic. I also have to mention that I'm actually working in an institute where we have a very strong computer science department. So we have been working with them on this machine learning topic for quite a while now, and this also spurred my interest for the topic. Moreover, in the innovations that are linked to artificial intelligence in Europe actually grew very quickly. So the absolute number in 2010-2013 was about 20,000. And it's really a rapidly advancing technology. So it's worth looking into it and trying to see whether there is something interesting in that. And also, well, although some of you, most of you, I don't know, are based in the US, I want to make a point that Europe is not lagging behind when it comes to the geographical spread of artificial intelligence. As you can see there, right? The US is the blue line, Europe is the yellow one, and in 2017, it was pretty much the same interest was in Europe and in the US. And in fact, the European Commission, when they planned the Horizon Europe 2021-2027 program, which is the way that they finance research in Europe, they planned at least 7 billion euros in projects which are AI related. So, you know, huge interest and highly policy relevant. But what is AI? So AI is a loose term and is used to describe technology that exhibit human-like intelligence. So as I mentioned before, machine learning is one of them, but think about also neural networks, or computer vision is another one that probably most of you can think of, but also autonomous robotics, and we go to things like also the AI-enabled traffic lights, right, which could help with traffic flows. Why is AI interesting and different? Well, AI has certain characteristics, certain, let's call them idiosyncratic features that make it different from other more traditional technology. First of all, is what it's called the general purpose technology. So it's not a specific technology, something that you apply to other technologies. And for the same reason, has also been called the invention of a method of inventing. So a research tool itself, which is capable to change the procedure for innovation. So in a sense, it's transformative, disruptive, and enabling. So we expect AI to have, and already in part already has, an expected huge economic impact. And what kind of economic impact can AI have? Well, on employment and skills, on productivity, on profitability and firm growth. And let's say that the most up-to-date book on the economics of artificial intelligence is this book published in 2019 by Agrawal and et al. So if you don't know it, and if you are interested in this topic, I would suggest that you actually have a look at it. But what about, why are we looking at AI and green technology? Because it has been said several times that the idiosyncratic feature of AI seem to be particularly relevant for environmental sustainability. In fact, there's been few studies in reality made not by academics, but by consultancy companies that show that if you ask a business manager about the potential of AI for environmental sustainability, almost all of them agree that AI has a lot of potential for environmental problems and could help solve them. So this was a report by Intel. Okay, there might be some conflict of interest here, but so they interviewed 200 business decision makers. About 74 of them mentioned AI as a hugely important tool for environmental sustainability, and it's also mentioned in their corporate sustainability reports. Of course, also international organizations have recognized this link between AI and environmental sustainability. For instance, the World Economic Forum or the European Commission itself said that artificial intelligence can transform industries and make them more green. Okay. So there was this report published in 2018 by the World Economic Forum, which was called Harnessing Artificial Intelligence for the Earth. And these were just examples of different fields in which AI was supposedly helping making the environment better, from climate change to weather and disaster resilience, water security, clean air, healthy oceans. This also is a very interesting report, but I'm not going into details because I don't have much time. Yet, despite the hype and recognized potential for AI for environmental sustainability, the impact of AI on eco-innovation has really not been studied yet. And most of all, the regional dimension of these links is often overlooked. So the aim of our contribution is to explore this link between AI and eco-innovation at regional level in order to answer these questions. So does a regional endowment of AI actually help their green transition? And then of course you have sub-questions to that, but this is the main point of the paper. We combine two data sources, which are the APO patents and the European Regional Database by Cambridge Econometrics to have economic indicators. We cover a quite long time period, 1982-2013, and we aggregated in 8 4-year period. And the geographical coverage is the EU 28, which you have a map there to have an idea of which countries are included. The technological coverage is the so-called CPC, technological classes at 4 digits. This is very well known among innovation economists, maybe a little bit less about among regional economists. So I had to get familiar to that. And so basically, these are the categories that are included, all the ones that started with Y02. And this is quite common. So this definition, it's not something we invented, it's something that we borrow from other contribution. And the final sample is about 482,310 observations at NUTS3 level by CPC by year, by period. So our dependent variable is what it's called, what it's well known in innovation literature as the green reveal technology advantage. You have to think of it as a sort of location quotient of green technology. So if a region is specialized in this green technology, i.e. has a revealed technology advantage in the green sector, green innovation, then this index is more than 1, and it's 0, and it's less if it's not specialized. We dichotomize it, so we have 1, 0, 1 if the NUTS3 region is specialized, 0 otherwise. This is just to give you an idea of the percentages of ones by country. So for instance, if you look at Italy, 14.56% of the NUTS3 regions in Italy are actually specialized in green technology. Well, France is 10% in honor of Sandy. If you want to look at Austria, very similar to actually Italy, not that different. What is our focus variable? Well, we want to study the relationship between AI and green innovation. So our focus variable is the stock of AI-related patents. It's not a flow, it's a stock, because unfortunately, we don't have yet many patents which are classified as AI patents. So we have to create a stock variable to have some sort of significance. Otherwise, we would have a lot of zeros. And this is a drawback of the paper that we've discussed quite extensively in the manuscript. But it's widely accepted that you can do that actually. And we define AI technologies according to, as I said, a series of papers. In the manuscript, we also have a series of robustness check in which we actually change the definition of our focus variable to see whether these might change our results. This is the first granular mapping of AI at NUTS3 level. Because it's not so easy to actually do it. And normally all the contributions look at larger geographical units such as NUTS2 regions. So this is how the AI stock looks like by region. Of course, the darker it is, the more dense is the AI stock in that particular region. And as you can see, there are fewer hotspots of AI patents than, say, regional eco-innovation. And then, of course, we have to control for all the variables that are commonly used in the innovation literature to explain the eco-innovation in a region. So, of course, we have lag dependent and focus variable, because this is the famous path dependence that almost every innovation studies find in terms of green innovation. We also have the patent stock in general, so the regional stock of patents of any technological field, because this gives you a vocation of that particular region. And then, most importantly, the first variable, we also look at technological relatedness, as it was defined by Boschma and Rigby in 2015. And this relatedness, I don't know if you are familiar with this concept, but basically it tells you how many sectors could be, let's say, close in terms of technological content to the green sector. This is just a very easy way of putting it, but of course, if you have read anything by Ron Boschma, you know what relatedness really means. All right, okay, so my clock says 13 minutes, so I still have 7 minutes to go through my results, and so maybe I can take a breath here and relax a little bit. Let's say that we start with a baseline empirical specification, which is the one that all the variable included that I just explained to you. And so this is a linear probability model. We also did a logit. As you know, there are different schools, whether you should use a linear probability model or a logit when you have a 0-1 dependent variable, but we did both. Here I'm only presenting the linear probability model, but there isn't so much difference. With a three-way fixed effect, the standard errors are clustered at regional and technological level. The baseline specification was then enriched with a series of interaction terms, and I'll show you in a second the results, and I'll explain why these interaction terms were important. But for instance, the interaction term between the lagged green revealed technology advantage and the relatedness answers the question, does relatedness reinforce the green tech path dependence, or it doesn't? Then we had the interaction between the green reveal technology lagged and the AI stock lagged. And again, this was to answer the question, does the green tech impact of AI benefit from pre-existing green experience or rather work for the green switch? Then we interact the AI stock with relatedness. So does AI attenuate the binding role of related technology for green tech specialization or rather make it more compelling? And the last one is actually a three-way interaction. And this answers the question, does the pre-existing green tech of regions affect the moderating role exerted by AI on related technologies for the green tech specialization? So I just put there the questions because sometimes it's a little bit difficult to get around the interaction term, especially when you do a three-way interaction term. Okay, so here are our preliminary results at NUTS3 level. And as you can see, there are some, I'm starting with the control variable first. These are not surprising results in the innovation literature because it's what everybody finds. So we're happy in a sense to have found that because it means that we don't have anything so counterintuitive in terms of the standard literature on eco-innovation. And so when you look at the lagged variable for green RTI, it means basically that the green text specialization is both path and plate dependent. So if a region is already specialized in a green innovation, then it's more likely that it keeps on being specialized in that. And the same for relatedness. If in the region you have a lot of industries which are somehow related close to eco sectors, again, this fosters the green innovation. So nothing really surprising or shocking in these results on the control variable. Moreover, relatedness reinforces the path dependence of the green tech specialization. So the two of them were positive. If you interact them, right, there is a reinforcing mechanism. Again, this is commonly found in the literature, so we were happy that this interaction term also was positive and significant. However, and this is the most interesting part of our paper, the one that then we discussed quite a bit in the results section, the AI stock does not seem to be positively related with the green tech specialization of a region. So an unconditional endowment of AI leads a region to prioritize other technology, almost escaping from green ones, okay? I'll give you a sense of why we think this is the case, but keep in mind these results because this is really what is important in our paper and what is surprising maybe to some in our paper, but we actually think it's important. Unless, of course, in regions that were already specialized in green technology, then AI might help. So the regional AI favors the green tech specialization only if a region was already green. And AI does moderate the role of relatedness, but this is not something really we want to focus on so much. But it does not attenuate the binding role of relatedness in already green tech region. just to show that we actually redid the analysis for robustness, of course, for the modifiable area unit problem, also at NUTS2 regions, and the main results stayed the same. It was only the three-way interaction and AI relatedness that became non-significant. But the main result that artificial intelligence is negatively linked to the green specialization of a region was very strong and stayed the same. And this is a distribution of the regional fixed effect, where you can start thinking about what it might be missing, and we think is some kind of institutional quality here that we have to put in, given the structure of the regional fixed effect, which are significant. Okay, so still have 2 minutes to get to the 20 minutes. So let me talk a little bit about the main results that we find. So we found that the relationship between artificial intelligence and green innovation is for sure not as straightforward as it is expected. Everybody talks about artificial intelligence helping a region become green or industry becoming more sustainable. Well, we find the opposite. But then we started talking with people that are experts in artificial intelligence, especially the computer scientists that I'm working with, and it kind of made sense to them because, say, machine learning techniques or the artificial intelligence in general needs a lot of data as an input. So it looks like they might be more applicable to certain manufacturing sectors, which are not really green sectors. I don't know, automotive, for instance, the so-called brown sectors, or at least not colored, kind of, let's call them white sector, rather than green sectors, because these sectors are generally newer. And that's also why we think that the other results make sense. If a region is already green, has already a green reveal technology advantage, so in a sense has a history in the green technology, then AI helps. So what we want to do next, there are other important dimensions that are missing, for instance, the concept of economic complexity a la Hidalgo and so on. But we want to explore this issue of the maturity of a technology. And so there are some data that allow us to kind of divide the green patents into kind of more mature sectors and less mature sectors. And we want to see if this is really the story that we want to tell, if it's really this lack of large data or historical data in the green sector that it's actually not helping the implementation of AI tools. 21 minutes, sorry, I got over.
Perfect timing, Alessandra. No,
Thank
great.
you very much.
Thank you so much. It's a very interesting topic and application. There is obviously a very large number of studies already looking at the knowledge production function of grillishes, but it is so innovative to be focusing on a question for which the data are kind of slowly building up. So, you know, it's just fantastic to be at the very early stage of that application. Now, I have a few comments for you and questions, kind of clarification and questions. So number one, is it possible that you give us a sense of what is the share of artificial intelligence focusing on environmental questions relatively to other topics? You kind of touched upon that at the end, but I don't have a good sense of it. In other words, do we see that AI is mostly focusing, say, on defense or transportation or other things? So were you to eventually indicate somewhere some stats on that could help? Secondly, some element that I believe I have seen in other application of grillishes production function will be, for instance, human capital as part of the input. Now, obviously, you may not necessarily have in a European context employment in AI focusing specifically on this, but eventually just a number of computer engineers in a region, something along those lines. Secondly, I wonder if there is any interest at all to try to account for other forms of investment that a region does for environmental purposes. In other words, an area may be very much caring about environmental issues, simply have not focused on AI per se, but they already may have some natural amenities that really push them to care more about the environment than otherwise. So I'm wondering if it's something to account for. I'm quite curious as to whether it will make sense to be focusing for the dependent variable on not only patenting, but actually spending for research in AI. The reason being, as you know very well, it takes many years in some cases for a patent to actually take place. In a US context, as I was focusing on similar questions, we discovered that in some cases it can be just 2 years, but in some others it could be up to 9 years. So the actual patenting may be very much delayed compared to spending in research. And then final question, as you are extremely aware, of course, you know, so special units are connected with each other. And I wonder if some of the work by Riccardo Crescenzi, who's looking at co-patenting between researchers who eventually live in different regions is something to care about, or the approach I use for the US case where we're looking at if the patent you develop in one area is actually based on the patent that was developed in the past in a different area. Now, I totally understand that the process being so new in Europe, maybe this kind of you know, network of patenting is simply not there yet. But no matter what, I'll be very happy to hear your thoughts about eventually including those elements.
Okay, so I'll start with the easiest one, which is your third one, the spending research on AI. We're already thinking about a way of changing the dependent variable because we are all aware, especially me. I mean, I'm working with the people that do innovation studies, and they're very keen on patents. They are aware of the limitations, but this is their you know, their goal. They really like this data. Me being a regional economist, I always think that the shortcomings are so much that I'm always trying to say, okay, can we do something else? We were actually thinking maybe if we could get data from the Community Innovation Survey to get an alternative to patenting, especially for more rural areas, because patenting in rural areas work very badly. But of course, we can instead looking at the spending in research. But this was definitely something that it was one of our priority in our list. Percentage of AI that focus on environmental, I would say it's very small. In reality, the percentage of AI patents in general is very small. It's still a tiny fraction, which was kind of the push for us to use a stock variable rather than use a flow, which also goes with your last comment, the co-patenting, but especially the network of patenting. We are waiting for the new data to come out. Maybe there will be a little bit more in terms of numerosity, more to go with, because so here is the real issue, right? You have an idea and you know that your data though are still quite sparse. So it's not clear whether you just wait another 5 years and then someone else will start coming out with this idea and have more data, or you just go, okay, is there a way that I can start looking at this phenomenon, even though the number of patents in AI, it's still not much. So the percentage is very small. Top of my head, I don't remember what's the percentage of artificial intelligence patents that are actually linked to eco-innovation. I don't expect it to be very high though. On the labor market, that's very interesting actually, because as you know, I do a lot of work on human capital. And this point that you raise about the engineers, to be completely honest, we hadn't thought about it, but it's something that we could easily, I think, find and put in some kind of human capital in terms of, you know, occupation, not so much education, but occupation, as you said, is something that I've actually written down in my notes, and I'll probably discuss with my co-authors whether we can implement it. And we have the data at NUTS 3 regions. We might not have it for all of the countries that are in, we don't know, but probably yes. Probably we can broad categories, not so maybe specific.
Yeah,
but we can
I'm afraid it's not going to go to that level, but maybe computer engineers eventually. So, but you know, Alessandra, it's so exciting to be at the early stage of a field. So congratulations for jumping on a beautiful topic. Why don't we collect more questions and comments for Alessandra, please?
Alessandra, thank you very much for a nice presentation. One sort of concern, not concern so much as lacking the information, what sort of training do you think we should be redirecting our students towards so that they can work in this area? Is it basically doing the same stuff, or do we have to sort of modify our modeling approaches? In particular, the sort of comments that Sandy was raised about the gaps between a patent and its adoption. It seems to me that we're going to have to spend a lot more time looking at the time dimension as well as the spatial dimension. So I wondered, based on your experience in the last few years, if you've got some thoughts on that.
Hi, Jeff. Thank you for your question. You mean training to use artificial intelligence, training to actually study this phenomena? Both?
Yeah, all of the above. I mean, is it just basically a different thing that we can apply our current toolbox, or are we going to have to modify it? And in which case, what sort of modifications are necessary?
So, okay, I do believe that the patents need to be, I mean, if I say substitutes, the 3 co-authors of mine, thank God they're not here, they'll kill me because they do innovation studies and they find patents really to be a good proxy. I personally believe that a lot of the innovation is not captured, and even this AI type of innovation, I don't know if it's really captured by patents. So for sure, we do have to collect better data and having different tools to capture this. I also do, as you know, Jeff, a lot of work on peripheral areas, and I get very frustrated because unrelated to AI, when I'm trying to study innovation in more peripheral areas, and there is some innovation there, it's not captured by patents at all. It's less maybe radical than what is captured by but there is a lot of stuff going on there that I would call innovative and is not captured. So that is something we need to really clearly think about. In terms of actually the students that I'm working with and that are working on this topic, I think that to study this phenomenon that I'm studying now, we need more interdisciplinary work. I find it very fascinating to study this and then work with computer scientists, because they give me a completely different perspective, and you know, they also give you some useful tool. I had a student that was working with machine learning algorithm, and he was applying that to the resilience of regions. So, you know, a really regional topic, and also having an idea of how these things work. It's then a big help when you go and study these kind of topics like I'm doing. So knowing a little bit how they work and what they are helps you think, okay, I do need a lot of big data for this. So maybe that's the reason why I found the brown rather than the green. But we do need to, it's a very complex topic. I think topics are becoming more and more complex, and we do need more interdisciplinary between us and other subjects. I don't know if this answered your questions.
Okay, thank you so much, Alessandra. We are going to move from Italy to Austria, and we're going to have presentation number 2. Presentation number 2 is by Professor Stefan Borsky. He belongs to the Wegener Center for Climate and Global Change at the University of Graz. And as you will see from the slides he's about to show us here, he's going to focus on the transmission of weather shocks in a global supply chain. So Stefan, I can see your slide, and I believe I can hear you just fine.
Okay,
so
do you hear me?
All yours. Yeah, I can hear you just fine.
Okay.
All yours,
Great,
Stefan.
great.
Thank you so much.
Thank you very much. Yeah, so first of all, I want to thank you everybody to give me a chance to speak in this nice seminar. And so what I'm going to present today is a joint work with Martin Uri, which is also research in my department at the University of Graz in Austria. And so what we're dealing in this paper is so we're looking at the role of global supply chains and how they transmit how they potentially transmit weather-induced production shocks through the supply chain indirectly to other countries. And so before I start, I have to note that this research was funded by European Union Horizon 2020 project and by the Austrian Climate and Energy Fund, which in some way give us some money to do this research here. Okay, so economies today are organized in fine interwoven networks of production units. Okay, so if we look how they are built up today, so input-output connections are very complex and globalized. And so if you have a shock in such a system in one country, like for example a natural disaster, then it can be widely dispersed through the economy through these inter-industry linkages. And there are a couple of prominent examples. For example, there's this 2011 flood in Thailand, which was a devastating flood, and it was affecting, especially the Bangkok area of Thailand, and around Bangkok there were about 15,000 companies which were in this inundated area and were affected by the flood. So in some way, in Thailand was a very large direct effect, but due to the fact that in this area were a large amount of automotive industries and computer companies were situated. First of all, for example, Toyota and Nissan had to decrease production worldwide because of a lack of inputs. And another effect was a doubling of global hard disk prices, okay, for a specific period of time. So in some way, this direct effect spread out worldwide. Another example is the 2011 Tohoku earthquake in Japan, which was this compound effect of an earthquake, a tsunami, and a nuclear accident. And it was affecting the northeastern part of Japan. And again, it has a large effect on Japan, but there is also studies which estimate that it resulted in a 1% production decrease in the US manufacturing industries for the month following this disaster. And the reason is behind this effect was that just a lot of these US manufacturing industries are strongly connected in their supply chain with these Japanese industries which were affected by this disaster. Overall, the extent of this effect more or less depends on the in-degree and out-degree distribution of the production network. So the stronger the connectivity between the production units, the stronger the effect. So from an empirical perspective, we have to ask ourselves, so is this are these two examples I gave you, are this just anecdotal evidence, or do we find like a systematic effect of this of the supply chain in transmitting these shocks worldwide? And so we are not the only ones dealing with this topic. Okay, there's quite a broad literature on this topic, and it can be more or less, the empirical literature can be divided into two parts. So on the one hand, there's empirical papers looking at the shock, the shock propagation networks across sectors within one country or across sectors between many countries. And for example, there's the paper of Buzzello and Rashki, and he's using the WIOD data, which is a multi-regional input-output data set, having more or less like country groups. So they're combining. They have some individual countries, and then they have also bigger country groups. And they were finding this large, significant negative effect. Then another strand of literature is actually the literature working on firm level and looking at this firm level impacts, firm level propagation of shocks within one sector, or within one sector in country, or between two countries, more or less. So, for example, this is paper of Parot and Sauvon in 2016, or the paper of Cavallo in 2016, which are the first looking at US data and the others looking at Japanese data, and they find that companies are transmitting within a country, transmitting a shock to the next to their customers, more or less. So, and then the other two papers, the Kashiwagi paper et al. In 2018 and the Böhm paper in 2019. So they do it more or less on a two countries like base, which the Böhm paper is looking at this Japanese-US relationship, and they find that that shocks can be transmitted over internationally, whereas the Kashiwagi paper do not find international transmission of shocks. And the reason is that that companies in some way internationally have more substitution possibilities. Okay, they find other ways to get their input supply, and so in some way their result in some way supports this Lucas critique that so in the aggregate everything is in some way balancing out. So based on this setting, our paper has a bit of a different focus. So what we were trying to do in our paper is, so we were trying to get as many countries as possible to get in some way the more or less full global connectivity between the countries and sectors. And so what we use is we base our analysis on sectoral level, and we use the input-output linkages from the Euro Global Supply Chain database. And the advantage of this database is that it has just a very broad coverage. Okay, so it has many countries, more or less all countries worldwide, and they have it for a long time frame, which is 1990 to 2015. And the second thing what we do is actually we were looking, our what we wanted to do is we not only wanted to take historic shocks into account, but we also wanted to get some knowledge or some idea about what's happening in future. And so in some way to project shocks in future, we needed to construct our own extreme weather indices, and we are basing this on daily temperature and precipitation data. So in what we do is we use a large global data set, and then we look at projections into the future. Just a short preview on the results. So what I'm going to show you is that these supply chain disruptions cause significantly reduces a sector's export value, and this effect is this negative effect is mainly driven by the manufacturing sector. What we also find is that due to climate change, these effects will grow in the future, but it will not be uniquely distributed or identically distributed in all countries, but in some way will cluster. And especially these countries which are within a region which is strongly affected by climate change, these countries are then also very much affected by these indirect supply chain shocks because of their interregional supply chain. And so why do we care about this? So what we observe is that our supply chains are more and more globalized, and this means that that shocks are more and more exposing globally. And so what we have seen in some way, the current COVID crisis have shown us how strongly a shock can transmit over the supply chain. A reduction in input production in China more or less affects many industries in Europe and the US by just having, so in some way they had to scale down because they were just not getting their inputs. And these shocks can happen all over, and it's not that they're just very, very, very scarcely. And actually, the frequency, the intensity of shocks will increase in future due to climate change. For example, in 2018, we had about 350 natural disasters worldwide, which resulted in around 11,000 deaths and 68 million people which were affected. And it was about a $130 billion US direct damage. So there are a lot of shocks which can be very devastating. And in some way, they don't have just this direct effect, but they also have this transmitting effect. And finally, what we also get is we get a one additional jigsaw puzzle piece to explain the macro how disasters affect macroeconomic outcomes, which is still not actually really clear in the empirical literature, and because it's just very, very difficult to identify. And so what we have to do is we have to really break up the economy and look at the different mechanisms to understand how disasters can affect macroeconomic outcomes. And in some way, this supply chain transmission shows one indirect effect. So conceptually, natural disasters affect the productivity level of firms in many different ways. Okay, so it destroys tangible assets, it affects labor supply, and it also has demand effects. And when you have economies of scale industries, then this also affects the productivity of companies. And so when the productivity of a company is shocked, this shock can be transmitted over the supply chain downstream or to downstream firms or upstream firms. the downstream effect runs more or less over two channels. On the one hand, if firm X, which is the directly impacted firm of the productivity shock, reduces production, it will increase their price. And due to a higher price, this will affect the downstream firm because their inputs are getting more expensive or more scarce, and so they have to scale back production. On the other hand, due to the fact that the downstream firm is facing a higher price, they start to substitute the higher input, the now more expensive input, with other factors of production like labor. And depending on the substitution elasticity of these factory inputs, it will also affect their productivity. From an upstream perspective, if the directly affected firm is getting more expensive, the demand for this firm is also reducing, and so this firm also produces less. Okay, so the directly affected firm is not so attractive anymore, and so they sell less, and so they also produce less. And due to the reduction in and by this they reduce their demand for input, which affects the firm upstream. Okay, so in some way this is the conceptual idea how productivity shock can affect firms upstream and downstream of the supply chain. The propagation effect by itself decays in distance. Okay, so from a network perspective, so the more nodes are between two firms, the less of importance are in this input-output relationship. Okay. So in some way, yeah. So this more or less sums up the idea how these shocks can be transported over the supply chain. Okay, so what we do is we have a very generic empirical model where we regress the logged export value of a sector H in country I and year T on our measure of supply chain shocks in sector H, I, T, and a set of control variables and a set of fixed effects. Okay, so we have sector year dummies, which more or less control sector-specific yearly factors which could affect the export performance of a country, for example, like business cycles. We have country year we have sector country dummies, which controls for sector specificities in a country. For example, if a specific sector in one country is very capital intense, then it can react differently to a disaster shock than other countries, than other sectors. And then we have country year dummies, which more or less control for everything that's happening in the country in a year, which affects the export value. For example, if a disaster is happening at home and not abroad. So what we are interested in is we are interested in this indirect effect. You know, the disaster happening somewhere else, coming then to our place. So our parameter of interest is this supply chain shock measure, which we have to create. And to create this measure, we need two pieces of information. On the one hand, we need to get an idea about how sectors are connected over the supply chain. Okay, and so what I've said before, so what we use is we use the EOROS global supply chain database, which is more or less a multi-regional input-output database covering 170 countries and 25 years. And so what we do then is we use the Leon-Dief-Inverse framework to classify each country's sector according to its degree of spatial connectivity. Okay, so the Leon-Dief-Inverse gives us in some way the sum of all direct and indirect amount of inputs used in one sector's production from all other sectors. Okay, so by this in some way we're able to get a matrix which gives us a classification of each sector and how this sector is spatially connected or in the network. Our second piece of information is actually our extreme weather events measure. And due to the fact that we would like to project it, we needed to create an extreme weather index, more or less. So what we do is, and this is now a couple of steps, and I hope it's in some way clear, but I will also try to be a bit brief because I'm running out of time now, and I have not even shown you the results now. So what we start is with daily 2-meter air temperature and precipitation rates measured at a half degree grid. Okay, so what we have is for the whole world is we have on a half degree grid the temperature and the precipitation rate every day. And based on these daily temperature measures, we determine monthly climate extreme indices at the grid point scale. Okay, and the indices what we chose are coming from the World Meteorological Organization. They have an expert team on climate, on sectoral climate indices, and we just use their recommendation, which is more or less a set of, I think, 26 indices. For example, heat days in a month, above a specific threshold, cold spells, and so on and so on. And so we are still at the grid point. So what we have to do now in the next step is, because our supply chain measure is at the country level, is we have to aggregate it to a country, to the country level. So what we do is we do it in 3 different ways. On the one hand, we take an unweighted mean. Then we use a minimum maximum, depending what makes more sense, or a minimum for cold wave and a maximum for heat wave. And a population weighted mean, where we take the spatial distribution of population in the country and weight the monthly climate extreme indices by this population weight. So in some way to account that it makes a difference if you have a flood in an area where many people are living, or you have a flood in an area where nobody is living. And so then what we then have is we have monthly country level, so a set of monthly country level indices, which are actually quite many. And what we do then is we calculate standardized anomalies. So in some way, what we do is we look at long-term means, monthly means, and see how our measure deviates from the long-term monthly means, and takes measure it in standard deviations for the period from 1990 to 2015. At the end, and so I told you it's many steps. At the end, we have created a disaster time series of all these different indices, and we just use these indices which pass a specific percentage threshold. Okay, so 90%, 95, and so on and so forth. And finally, and now we have many of 100 indices. What we do is to select some indices which are, no, they are all super highly correlated with each other. So what we need to do is we need to select some indices which explains a potential disaster in the country. And what we do is we cross-validated our indices with a database which is covering disasters worldwide, which is called the Emergency Event Database, EM database, and see how good are our disasters predicting disasters based in their database. Okay, and then finally we get a small set of disaster indices which are more or less which were the best indices explaining disasters in their data set. Okay, very quickly, we also did the same for the future, but for the future we use different data sets. So we use temperature and precipitation data on 5 global circulation models, because the problem is we have the whole world, and so global climate models or global circulation models are very different depending what world region you're looking at. We use 2 mission scenarios, the RCP 2.6 and RCP 4.5. These are scenarios which in some way explain you climate futures. And RCP 2.6 climate future is a very strict climate change future, which more or less results in a 1.5 degree increase in 2100. And RCP 4.5 future, climate future is an intermediate climate future, okay, having a stronger climate change effect. We also have a model for the population dynamics, which we needed for this population weighted indices, and this is coming from the shared source again, McBath V2. And then finally we did the same procedure again as we did for the historic data for the future. Okay, so now what we have is we have now these 2 pieces of information, that the weather extreme indices and the connectivity. And then just if you plot this information, then we see it here. So it's 2 pictures. On the left hand side you see the year 2005. On the right hand side you see the year 2015. The Y in the x-axis shows you the backward and forward linkages of sectors. Okay, so the higher the number, the more strongly are sectors exposed into the supply chain. Okay, so there's like a rule of thumb: when sectors are exposed, when the value is higher than 1, then sectors are strongly exposed into the supply chain. The red axis, so that is the red crosses, gives you sectors and countries which are affected by disaster in that year. And what you see in some in this picture is that we have many sectors, or that we have sectors which first are very exposed in the supply chain, with backward and forward linkages, and second are receiving a natural disaster shock or an extreme weather shock. And so they have a large potential to transmit shocks. Okay, and we have this for every year. Okay, so what we do now is we use these two pieces of information to construct our index. And our index, so what we do is we combine each element of our connectivity matrix with the vector of natural disasters in country J, so in the other countries abroad. And so what we get at the end is what our supply chain shock index tells us is the proportion of inputs which are potentially affected by natural disaster for a sector in a country. Okay, and what you see is that this index is in some way affected by two things. So on the one hand, the higher the exposure into the supply chain, or the higher the connectivity, the supply chain connectivity of a sector with other sectors, the higher our supply chain shock measure, and the more natural disaster shocks these sectors have, also the higher our supply chain measures. Okay, so in some way it's affected by the connectivity and how strongly are these sectors with which you're connected, how strongly are they affected by disasters. Okay, so I will jump over it. And so what you see here is just when we do our regression. So what you see is that our measure for supply chain shock index is significant for all different model specifications, and we just concentrate on model 2, which is our preferred model specification. And what it tells us that a 10 percentage point increase in our supply chain shock index decreases the export value of a country's sector by 3%. Okay, and this number is more or less the same if you put different controls in it, or a different set of other robustness exercises. What we did in the next step is actually we were interested, okay, is this effect the same for all sectors, or do we find sectoral differences? And so what we did is we grouped our sectors into bigger sector groups, which were agriculture, manufacturing, energy, and mining, and we're doing the same regression analysis again. And what we see is that our effect is mainly driven by the manufacturing sector, and this also makes sense because this is especially the sector which is first of all very extended in their input outsourcing. So they have a high extended input outsourcing, so they're very exposed globally to the supply chain, and they also have a large vertical depth in the supply chain. Okay, so they have very often many trading partners, and that's the reason why they are also so much exposed to shocks in the supply chain. Okay, so what we did in the next step is then we started to do the projections. Okay, and so to do the projections, we proceeded in the following way. So we used our regression coefficient, what I just have shown you before, and multiplied it with the difference in our supply chain shock measure from the baseline, which we have calculated before historically, to the future. Okay, so what we do is we calculate our supply chain shock measure for all different future periods, so actually for every year in the future, and then we just take the difference between the baseline supply chain shock and the future supply chain shock, and then multiplied it by the regression coefficient. So in some way, so the result of this exercise can be interpreted as an additional climate change effect on the supply chain shock measure, or the supply chain shock extent. Okay. However, this procedure is actually based on very strong assumptions, and so what we do is we keep our input-output structure the same for all the years. Okay, so we take the input-output structure for 2015 because we don't know the input-output structure in 100 years, so we take it fixed on 2015 levels, and so the only thing what's changing actually is the extent of extreme weather shocks. Okay, so so by this we get a measure of a future where no adaptation takes place. Adaptation in a way that the supply chain can adapt to changes, to shocks. Okay, so they can redistribute in the supply chain. So so in some way our results must be interpreted as upper limits and upper limits for like in a worst case scenario, so when nothing is happening, so when we just do as we do now. And that's for sure a limitation, and actually that's actually what we're working on now. And so what we see here is on the left hand side, you see the projected impacts when we for a climate future which is a strict regulation, but it's 1.5 degree target. On the right hand side, you see it for climate future with intermediate climate change. And the green line is the distribution of shocks for the time period 2020 to 2040. The red line is for 2041 to 2070, and the blue line is for 2071 to 2100. And so what we see is more or less, we see two things in these pictures. So first of all, in these figures, we see that the spread of impact is quite strong. Okay, we see a huge heterogeneity in impact for sector and countries. And the reason is because sectors are differently exposed to shocks. So first of all, it depends how strongly they are interconnected in the supply chain, and it depends how strongly the trading partners are affected by disasters. So what we see is that that the tails of the distribution reach from 0 to 20 in the closest period, and up to 25 minus 25% in the more future periods. What we also see is that the distribution of the impacts move to the left, to the more extreme, when we go deeper into future. Okay, and there's some way what climate change does is it pushes the distribution of the impacts to the far left and to the more extreme cases, to the more extreme values. What you can do is actually climate change will not only change the frequency of disasters, but it will also change the intensity of disasters. Okay, so we can do the same exercise now, but taking additionally the intensity of disasters into account. And we see more or less the same picture. Again, this huge heterogeneity, and then again this far spread, and also by climate change, this push to the left in the more extreme values of the order. Okay, and maybe also was the same picture before. What we see is that there's a huge difference between the RCP 2.6 and the RCP 4.5 scenario. Okay, so you see quite differences depending how strong the climate change effect is. Okay, so I have to close down. But so what we did is as another exercise is then we're thinking, so now before you were just seeing the distribution of the impacts for each sector and countries, and so then we were thinking, okay, so maybe it could be interesting to see which countries are on average especially affected by climate change and the other not. And so what we did is we just take the average effect for all sectors in the country and made a table for it. Okay, so the upper part of the table is the RCP 2.6 table, and the lower part is the RCP 4.5 scenario. And then again, we see these three different time periods, and then we just show the 5 countries with the highest impact and the 5 countries with the lowest impact. And so when we look at the lowest impact countries here and here, so we have it for every country more or less. But when you look at the countries with the lowest impact, you see these are especially countries which are either not very strongly exposed in the production network, like for example Afghanistan, or are placed in a region which is just not very much affected by climate change. Okay, for example, which are European Union countries. Okay, so European Union countries have, on the one hand, quite a large production network between the countries in the European Union, but all these countries are more or less not very much not so strongly affected by climate change. Okay, for example, you see Denmark, Slovenia, and so on. And when you make the list a little bit longer, you see the other European Union countries as well. On the other hand, if you look at the highest countries with the highest impact, it's especially the countries in the tropics and the subtropics. And the reason is not that these countries are so super strongly exposed to the global supply chain, but what is that these countries are actually situated in a region which is just very strongly affected by climate change. And so which means is that due to the interregional trade, they get indirectly a lot of these climate change shocks imported to the country itself. Okay, this is in some way an important message, important finding, because actually it's these countries which are already affected directly by climate change effects very strongly. They also receive now this very strong indirect effects because of their regional supply chain pattern. Okay. Yeah, that's just on maps. And so I will come to my conclusion. And so what we have seen is that the production of a final good in a country is based on numerous input-output interlinkages. And if you have a disturbance, it can propagate over the supply chain and leading indirectly to a change in other countries' macroeconomic outcomes. And what we have shown is that these shocks leads to large negative effects on a sector's export activity today as well as in future. And we have also shown you that some countries are affected stronger by disasters, simultaneously also have a strong position in the network. We also have seen, for example, that some countries or country groups which are affected, which are situated in a region which is very much strongly affected by disasters, are also sending in the interregional trade network their shocks indirectly to each other, and so on and so forth. Okay, just from an adaptation point of view, okay, what can firms do? And that's not very new, and I think this part can be a little bit more elaborative in future. But no, in some way, firms and industries need to be made aware of potential risk of supply chain disruptions. And what I think is they are already aware. Latest with the COVID crisis, because a lot of companies have seen that, okay, wow, now we are very much interregional exposed to shocks. And so in some way, what you hear very often in literature is that industries and firms have two choices. On the one hand, there's this argumentation, increased geographical diversification. But the problem is actually it's very often a very limited adaptation choice. When you zoom into a production process in the company and you want to find out where a specific input is produced, it's very often just produced by a handful of companies, and very often this handful of companies are spatially agglomerated, very often in the same country. Okay, so geographical diversification is sometimes just very, very difficult for countries, for industries. And the other adaptation measure you hear very often is actually, okay, so build storage facilities. But again, then you have the problem of the trade-off between storage costs and just-in-time production. So I leave it there. In some way, it's an open ending, but maybe we also come to some conclusions in the discussion about what can we do and what we can't do. Thank you.
Great, Stefan, thank you so much. It's a really exciting work. You know that most of the contributions that I have seen focusing on the impact of those extreme events at the international level really disregard any form of relationship between those countries, be it either trade like you do, or migration, or other mechanisms. So it's really exciting to see it's happening. It turned out that there is a bit of literature that's already out there that is focusing on fairly similar questions at the subnational level. For instance, in the US, we have a software called HAZOS, which is looking at the impact of disaster events within, the communities of the US. And they try their best. They don't necessarily do the best job ever, but they try their best to also account for this form of interregional business propagation of losses across different areas. So it's something that you may want to look at. Mm-hmm. There is also some other folks who have worked on similar questions at the subnational level. I'm thinking about Adam Rose in California. Jeff has done some work along those lines related to earthquake, Okuyama in Japan. So I'll send you a few things because I think there is something to learn from the subnational level and the propagation of those shocks through the supply chain, even so your focus is mostly at the international level. So the comments I have are mostly related to one element which is very difficult to deal with. And I think you really pinpoint to this question towards the end of your presentation. Obviously, those trade flows are measured at the yearly level. On the other hand, those events, and based on the data you have, are obviously at a much finer scale in terms of time, and even in terms of location. And you exactly pinpoint to one of the difficulties here, which is there is a huge, ideally, you will have a good sense with respect to where sectors are actually located in space and whether or not that weather event has taken place in exactly that location. An example quite famous is in the US, almost the entirety of the aircraft and aerospace industry is in Washington because of Boeing. And it turned out that even the suppliers of Boeing are located in Washington. So if if a weather event happens beyond Washington, it does not necessarily affect that sector. So one option that I can think of is this one. Number one, you could see if there is any way at all to get a sense of the level of spatial agglomeration of some of those sectors you're interested in, and get a better sense as to where they actually are located. I'm guessing it's going to be hard because you have a very large database, it's worldwide. So eventually option number two is to be relying on the IO table at the regional level, which exists in Europe. I forgot the name of it, but it seems that Europe has developed those interregional IO matrices at the NUTS2 level. In this case, I think it is not wrong to assume that if a weather event were to take place in one particular region, it will pretty much homogeneously affect all the industry of that area. Other elements that I think you may want to consider too is the question of the duration of the event. In other words, you may have extreme rainfall at some point during the year, but if it's only for one day, maybe it's not a big deal. I wonder if there is a way at all to include that duration aspect. I also wonder whether there is some interest into looking for the timing of the event. So for instance, when it comes to a flood, and if you focus on its impact on agriculture, it's not necessarily a big deal if the flood is taking place between the planting and the harvesting season. On the other hand, if it turns out that your flood is really happening a couple of weeks before you harvest, then it's definitely a huge disaster. So for some industries, not all, but mostly those which are ag related, I think that eventually looking at the timing of the event is something to be careful with. And then final comment for you, Stefan. You pinpointed to that too, that fact that, of course, nobody knows what the technology and production function will be like in 50 years from now. So here is one idea I have. You tell me if it makes sense or if it's total garbage. What if you were to calibrate your model on the very first year for which the exo-based data is available? I think it's 1990. You just calibrate it cross-section kind of approach. Then you calibrate a second model for the very final year. I believe it's 2014. I'm not sure anymore. Then you, based on that, you have a bit of a sense of how the marginal effect of your weather variable actually evolves in time over a period which is only 24 years. It's not amazing, but it's better than nothing. And eventually you could include that element as a potential change of what the technology is expected to give us in, let's say, the next 24 years, or you could even extrapolate it to the 50 years in the future that you're interested in. So what do you think, Stefan?
So first of all, thanks for a lot for this for all comments, and more or less I agree to everyone. Yeah. And yeah, so given the disaggregation points, yes to everything. So actually, in some way, when I started the project, I was thinking that it's very easy to find out where industries are located. And actually, what I found out is that it's not easy at all. Actually, there's based on my knowledge, I haven't found any data set which gives me a global picture on industries. And so that's the reason, for example, why I've started this the project proposal from Sandy to Sandy about this, where I wanted to find out where the industries in Europe are, because even in Europe we don't know really exactly at the point where the industries are. So to my defense, in some ways, that given that our sectors are quite big, I hope that we get some industry which is in the sector, so like a homogeneous distribution of the industries in the sector across the country, and so in some way we pick up the effect. So what would be the impact on the effect if we're not able to pick up the shock? So that would be that if you measure a shock in a place where not the industry, where the sector is not situated, then this would actually result in a null effect, more or less, so that there is no shock transmitted because there was no shock happening. And so in some way, by this, it helps a little bit in that way that we're some way on the here at the lower point of the estimate by just not getting these shocks. So we don't, I think we don't give wrong shocks to wrong sectors, but we just don't get the sector correctly shocked if this is the case. Then again, the same is with duration and timing. It's just we spend a long time on this. It's so difficult to start from the point estimate, and then at the end you have to end up at the aggregate country level, and from the year level. And then in some way you have to make some decision. Maybe we are able to measure the duration. We have it in somewhere in the indices as well. But yeah, and then again, timing of the event, I'm with you. That's very sector dependent. So in some way, a lot of information gets lost maybe about with the breadth of our study. So more focusing on one sector, maybe it gives you some, for sure, more information. You're able to deal with this much stronger way. The adaptation case is actually an interesting point. I think I know a paper of work from Schlenker and others, and they did it for the agriculture, and there's also this long-term differences. And I was a bit reluctant doing it, but now maybe I'm not reluctant so much anymore, because we just don't have so many years. But yeah, no, we have this. Yeah, so we have this 25 years. Maybe there's not enough time for measuring our adaptation thing, but for sure we get a glimpse how adaptation will work out. And in some way, I think it's necessary to put adaptation somewhere in these projections, because else it's just like very worst cases where nothing is happening.
No, but you're right, Stefan. It's definitely not an easy task. Great. Why don't we collect more questions and comments for Stefan, please? Okay, I think that some folks have gone for lunch or for dinner, depending on where they are. But Stefan, I would love that you send me the paper, because it's extremely interesting topic.
Sure.
I will forward you some work related to the people I listed for you. It's as I said, subnational level, but I think there is quite some interesting element to learn from them. So, well, with that, we're going to conclude. I want to thank very much Stefan from Austria, danke sehr. And I want to also thank very much Alessandra, Faggian, grazie mille. Thank you very much to both of you for a very interesting talk and presentation. And I hope to see all of you,
Sandy, for the invitation.
Yeah, thank you.
I hope to see all of you next week, same time and same place. Thank you very much.
Thank you. Bye. Bye.